All right, here we go. Again, after galaxies comes the expansion of the universe. So, the element of the day, one of three, I guess, is bismuth. Bismuth is the real dividing line in the periodic table of elements. Every element after it inevitably decays into other elements. There is no stable isotope. Two other elements before it decay as well, technetium and promethium. Every element before bismuth has an isotope that never decays, with the exception of technetium and promethium. So, barring outside interference, these elements will stay around until the end of time. Physicists have been nurturing a notion that protons might decay someday, but we sure have been watching for a long time, and it hasn't happened yet. Bismuth is famous. For example, Pepto-Bismol has as its active ingredient bismuth. When you chemically separate everything out, only bismuth remains. When an element's nucleus changes, when a proton leaves or arrives, the chemical properties almost completely change. This is because almost everything about the behavior of an element is determined by its electrons. You get one more proton, you get one more electron. You take a proton away, you get one less electron. Look to the left of bismuth. One proton less, lead, not healthy. Look to the right of bismuth, polonium. One more proton. Polonium is highly toxic and was used for assassinations relatively recently. It's what killed Alexander Litvinenko, who's the ex-KGB spy that died in London after somebody slipped some polonium into his tea. So the thing that cures your belly aches would be poisonous with just one less proton. That's how differently elements behave depending upon whether they can get an extra electron or whether or not they lose an electron. So, the cosmological principle. In theory, and this is just a guess, the laws of physics are the same everywhere in the universe. The universe is supposed to be homogeneous over large scales, which means it has the same composition everywhere you look. It's supposed to be isotropic over large scales, which means no matter which way you look out, it will look the same. Here's a homogeneous and an isotropic universe. Here's a universe that is not homogeneous and not isotropic. We would live in the universe to the left-hand side. Oh, come on. And we're back. Sorry, got a call from my child's hospital. All right, so just to kind of walk you through, wait, what happened to Olbers Paradox? All right, well, just to kind of walk you through our local situation. There's a local group, and you see three bright things circled. The two things that are close to each other are the Milky Way and Andromeda. The one that's a little further away is the Triangulum Galaxy, and those are the three major galaxies hanging out together close to us. We are being attracted towards a huge supercluster called the Virgo cluster. That is not going to succeed in getting us before the expansion of space-time separates all these things by so much that we can't even see them anymore because they're so far away that light from them can't reach us. There's the filament structure of the universe, voids and filaments, as are discussed in galaxies. All these bright things would be relatively large galaxies. The darker things are much smaller galaxies, so on and so forth. So, Olbers Paradox. Why is the sky dark at night? Well, if the universe was filled with galaxies in every direction, then we should see a sky that never knows darkness. It should always be bright with stars and different distant galaxies. When the size of a galaxy gets smaller with distance, the brightness of the galaxy gets smaller with distance. Thus, the amount of light per square inch in the sky should stay the same. So, in your forest, everywhere you look in a forest, you see a tree. Why do we not see galaxies in every direction that we look? There's one of two different explanations. Either the universe is not infinitely big, or the universe is not infinitely old. Both of these things are true to some extent. The universe is definitely not infinitely old, and we have no idea if the universe is infinitely big, and probably we never will, because the expansion of space is taking galaxies away from our field of vision so rapidly that there is absolutely no way for us to see the whole thing. We literally see galaxies get redshifted and redshifted and redshifted and then disappear from any telescope that can observe them ever. Once they're gone, you can't get there from here. I mean, we can't even travel close to fast enough to get there from here, but if we could suddenly travel at very, 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 very close to the speed of light, we could still never reach these galaxies that have receded to the point that they aren't visible anymore. So, how do astronomers measure distance to galaxies? Close by, you can use radar. There's not very many telescopes that are equipped to do this anymore. Arecibo used to be able to send out radar pulses and measure the return. I have no idea where a telescope exists that can still do this. Then we got parallax, spectroscopic parallax, which is a fancy name for redshifting and blue shifting. Further out, there's Cepheids, which I showed you in galaxies. There's a decreasing and increasing brightness associated with certain types of stars. We assume that all these stars are similar enough that they would pretty much all have the same physical properties. So when we can observe one, we know basically how far away the host galaxy is. And finally, there's type 1a supernova. Remember, that's when a white dwarf manages to accrete enough matter to be 1.4 times the current mass of the sun. Once a white dwarf gets that much matter, it just explodes. And we think that they all more or less explode equally brightly, although it seems that the metallicity of the white dwarf does matter in terms of how bright it is. Metallicity being a fancy word that astronomers use to indicate any element being present that is beyond helium. So, the main way we measure velocities of galaxies is through redshifting and blue shifting. Almost everything is going away from us. Only a few things are going towards us, the most notable of which would be Andromeda. Remember, it's going to hit us. And this would be how you calculate redshift, which you all can actually do. So lambda observed minus lambda emitted divided by lambda emitted is the main way that astronomers calculate redshift. If we were to hit chapter 44 in a mathematical kind of way, you guys would be doing this calculation over and over and over again. So z equals 0, galaxy is not moving. Z is greater than 0, galaxy is moving away from us. Z is less than 0, galaxy is moving towards us. But there's basically only a handful of galaxies that are doing that, and they're all very nearby. So here is the large-scale structure of the universe. We've got the Milky Way center, and here is every other big old cluster of stuff that we can see out there in the distance. Some of these are galaxies, some of these are clusters, some of these are superclusters, so on and so forth. So, yeah, the universe is isotropic, and the universe is homogeneous. Looks pretty much the same no matter which way you look, and the composition is pretty similar every way you look. You see superclusters and clusters and galaxies all over the sky in about the same density. Now that we know where galaxies are located, we can ask the question of how galaxies are moving. So these galaxies follow something called Hubble's law. And almost all galaxies appear to be moving away from us, with the only exception being Andromeda, Triangulum, and the rest of the little galaxies that are trapped in there with us from the massive gravity from the three main galaxies in our local cluster. So, does this violate the cosmological principle? Is the universe not homogeneous or isotropic? Nope. It's exactly the motion that should be observed if the entire universe is expanding at the same rate. So, here we have two different galaxies marked. In picture C, it's in the upper left. In picture D, it's in the center. And both galaxies perceive other galaxies as moving away from them just due to the fact that space-time itself is expanding. Just as a fun factoid, space-time is expanding inside of you. You are experiencing the expansion of space-time inside of your body right now. And so is the planet Earth, and so is the solar system. The thing that makes you different than systems of galaxies is that you are chemically very strongly bonded together. So is the planet Earth, and the solar system is gravitationally bonded together. The Milky Way is gravitationally bonded together. And even Triangulum, Andromeda, and the Milky Way are all gravitationally bonded together. That means the expansion of space-time results in the new space-time being created inside of these objects just dissipating out harmlessly. We're still held together by chemistry or by gravity, and so nothing bad happens. Here's another analogy. Everything on the ruler is getting bigger and bigger and bigger. The ant that started at 2 centimeters perceives the ant at 4 centimeters as being a little stronger. The ant at 7 centimeters is being much further, and the ant at 12 centimeters is being much, much further. Alternately, you can view this in a three-dimensional state as imagining raisin bread. As raisin bread cooks, the whole thing expands. The further away the raisins are from each other, the more they end up further from each other than they were when they started. So, raisin bread analogy, actual astronomical analogy. The uniform expansion of the universe yields Hubble's law. How fast is the universe expanding? Well, there's math for that. The Hubble constant is 70 kilometers per second per megaparsec. Parsec is about 3 light years. So if something's 10 megaparsecs away, then its speed relative to us is 700 kilometers per second. Still a fraction of the speed of light, very low. But if something is 1,000 megaparsecs away from us, then the speed relative to us is 70,000 kilometers per second. The speed of light itself being only 3.0 times 10 to the 8 kilometers per, 3.0 times 10 to the 5 kilometers per second. Starting to get up there. Once something's far enough away that its effective velocity from us is greater than the speed of light, it is no longer a part of our universe. It is a part of the universe, but we're never going to interact with it again in any way, shape, or form. So only nearby galaxies are moving towards us. Andromeda is going to hit us first. Eventually, we'll suck up Triangulum and all the other minor galaxies. Space is expanding, but anything that is gravitationally or chemically bounded together will not expand. So we observed two galaxies. Galaxy A has a redshift of 0.5. Galaxy B has a redshift of 2. Which galaxy is moving way faster? Think about it for a moment. It would be Galaxy B. Which galaxy is further away from us? Galaxy B. Because the reason it's moving way faster is not due to its actual velocity relative to the Milky Way. The reason it's moving way faster is that there's so much space-time in between us and it that the expansion of space-time gives it an effective velocity. If both galaxies had a supernova explode at exactly the same moment, which galaxy would astronomers on Earth see the supernova first? You would see it in Galaxy A. It's much closer. And which galaxy appears to be younger? That would be Galaxy B. It's further away. Light has had to make a long journey from Galaxy B to the Earth. Consequently, we're seeing Galaxy B at what is close to its infancy. Light from the sun takes about 8 minutes to reach Earth. So we see the sun as it appeared 8 minutes ago. And not just see it, but also feel the gravity from it. If the sun were to suddenly disappear, the Earth would continue in orbit around the spot where the sun used to be for 8 minutes. Because the propagation of light, as well as the propagation of gravity, is affected by the speed of light, which is just the maximum speed that information can propagate at in the universe. Light from the nearest star, Proxima Centauri, takes about 4 years to reach Earth. So we see Proxima Centauri exactly as it was 4 years ago. At a redshift of z equals 0.5, light from Galaxy A takes about 5 billion years to reach Earth. So we see Galaxy A as it was 5 billion years ago. At a redshift of z equals 2, Galaxy B takes about 10 billion years to reach Earth. So we see Galaxy B as it was 10 billion years ago. So what does Galaxy B look like now? We don't know. We can't know. We only see the light that reaches Earth, so distant galaxies always appear very young to us, since the light that is being emitted now will not reach Earth for another 10 billion years. So the further away a galaxy, the younger it looks. We study how galaxies evolve over time by comparing distant, very young galaxies to nearby, very old galaxies. And that's one of the tricks that astronomers use to try to figure out how the universe works. So this means we effectively can see back in time. Okay. How does the overall distribution of galaxies change over time? Well, as the universe expands, matter gets diluted. It gets spread out. If you imagine a movie of the universe expanding and then you reverse the movie, you see a universe shrinking back on into itself. This would be the Big Bang. So free electrons love nothing so much as absorbing photons. They would do it all day long, if they could. So when the entire universe was a plasma, we can't see what was happening. Light was being created in abundance, but it was always immediately being absorbed and re-radiated in a random direction by the free electrons. When the universe cooled down to the point at which the electrons actually got bound to atoms again, the universe was about 2,000, 3,000 Kelvin. It was basically red hot. a red hot, star, more or less, give or take. And we see that first light as being cosmic microwave background radiation. Now, the light itself that was emitted at the time was mainly red, but just as the universe's expansion has moved galaxies further away from each other, it has also shifted the wavelength of light so that the wavelength has gotten longer and longer and longer. Light from this recombination, when protons were able to have electrons attracted in orbit once more, was initially red. Now it's microwave. Quite a downshifting. After that, it took a while for stars to be born, but not that long. Within probably less than 1 billion years, stars were being created or falling into existence. Stars probably came before galaxies. The earliest stars seem to have been preferentially huge, and so they made a lot of new complicated matter when they exploded. And they also exploded pretty quickly, since huge stars do not live for all that long. So we'd like to figure out how old the universe is for various reasons. For a long time, we just kind of thought that the universe was this perfect system that wasn't really changing. It was static and unchanging. In 1920, the idea of the Big Bang was first proposed by Georges Lemaitre, a Belgian priest, astronomer, and physics professor. So you think about what the Big Bang means. At this point, you may be picturing a kind of explosion that sends a cloud of debris shooting through space. But it's not an explosion. Space itself is expanding, and the atoms in existence are moving along with it. You are as much the center of the Big Bang as the floor beneath you is, and the window to your room is, and everything else in the universe is. Every piece of space-time in existence is fundamentally the center of the Big Bang. That's just how space works. Since everything was once in a single point, we are all equally the center of that single point. And what is the universe expanding into? As far as we know, it's not expanding into anything. It's just expanding. We only know that the universe exists, and the universe contains everything that we know exists. So the universe is getting bigger, but there is no reason yet to assume that there is anything outside of the universe. So typically at this point, an astronomer professor would take a Sharpie, put a bunch of dots all over a balloon, and blow the balloon up. And then you'd see this. Everything's getting further away, and the things that are furthest from each other are getting further away the fastest. Where did the Big Bang take place? Everywhere. Every part of the universe was compressed tightly together in the same spot when the Big Bang occurred. Thus, everything in the universe experienced the Big Bang at the exact same time. And finally, I touched on this before, but can we see to the edge of the universe? First off, the universe doesn't have an edge. It's either infinite or else it curves back in on itself. We don't know which it is. But also, more and more and more of the universe is becoming invisible to us for forever, because the expansion of space-time is leading to objects in the universe effectively receding from us at more than the speed of light. And we're back. All right. So the universe is about 14 billion years old, give or take or give. So we can see everything contained in a bubble with a radius about 14 billion light years away from Earth, which does not mean in any way, shape, or form that we can see everything. So we know there's other stuff out there because we've seen it vanish. Like it's clearly on the way out. Things that are super far away from us are no longer visible. So how far in the universe can we see? And the answer is that we can see as far away as light has had time to travel in the age of the universe. But because the universe has been expanding while the light was traveling towards us, the exact distance to objects in the observable universe is actually bigger. I'm not going to play this YouTube video in case they have stronger protections than the Sacro lecture has, but please do check it out on your own. So, when we first saw the redshifts of galaxies, we thought the light was redshifted due to the Doppler effect, i.e. the galaxies were actually moving relative to us in space. And the further away things are, the more heavily redshifted they are. But pretty soon it became obvious that there was more going on than that. We can calculate exactly how hot the universe would have to be in order to have its electrons free and flying around all over the place. We know we wouldn't be able to see anything while the electrons are in that state. So we know for sure that the universe cooled off when it was 2,000 to 3,000 degrees Kelvin. And we know for sure what kind of light we should see from that, which is red. The universe is red hot. And we don't see that anymore. We see only microwave light. So it seems that as the universe has been expanding, all the light inside of it has been expanding as well. Wavelength has gotten longer. A lot longer. Long enough to turn red light into microwave light. So, is there really a difference between Doppler effect and cosmological redshift? Yeah. The galaxies that are moving truly towards us and truly away from us are not the same as the galaxies that are being separated from us by the expansion of space-time. In order to support or disprove the Big Bang theory, scientists examine the predictions made by this theory and gather evidence. One very important prediction of the Big Bang is that the universe began as a very, very, very small speck that was super hot and super dense that contained all of the matter in the universe. Let's look at what that prediction means for how the universe should evolve over time. The universe started out very hot, it cools. We know that hot, dense objects emit light in a characteristic blackbody spectrum. Super hot object, emitting mainly ultraviolet light. An object like our sun, emitting mainly green light. An object like a light bulb, emitting mainly infrared light. So when recombination happened, when those protons were actually able to grab onto their electrons, all of a sudden we could see things. Light can travel through neutral atoms. Space becomes transparent all of a sudden. In the ionized early universe, light was trapped by free electrons. It was bouncing around every which way. Radiation itself had a blackbody spectrum. This time it was kind of as if the universe was filled with a thick fog. At recombination, the universe became transparent. The light could travel in straight lines again, and the blackbody radiation traveled freely through the universe. Recombination would be like the fog suddenly clearing. The first atoms, complete with electrons bound to them, would have formed 40,000 years after the Big Bang. We have something called the Cosmic Dark Ages, before stars could really form. And then eventually we're at now. Stars and galaxies and all that stuff. Temperature of the universe has been going down and down and down since the very beginning. We don't really know for sure what the universe was like in its early history. This is a big part of the reason why particle accelerators exist. We want to slam things together at higher and higher speeds so as to figure out how matter behaves when matter hits matter at extremely high velocities. Remember, temperature is kind of a measure of how fast things are moving. So high velocities indicates high temperatures. Eventually, forces are unified, and by that I mean everything's far enough apart that the strong force has a different range than the weak force, has a different range than the electromagnetic force, has a different range than the gravitational force. Then there's kind of a long time when radiation dominates, by which I mean that energy goes bouncing all over the universe because electrons were just absorbing it and irradiating it. Protons and neutrons are made out of quarks, and those would be blasted to pieces the moment they tried to combine. Electrons, however, are leptons. Leptons are their own unitary thing. They really can't be destroyed. And so they've been around from the very beginning. So protons and antiprotons form, and then for some reason this graph says wrongly electrons and positrons form. Eventually atoms form. And then the graph says wrongly that galaxies form before stars form because stars happen before galaxies. We've already talked about this, but the light we're searching for is the black body spectrum of the early universe. We can figure out the temperature at which the universe has formed the first atoms. We can determine the expected shape of the black body spectrum, and that would be T is on the order of 3000 Kelvin. And then we account for expansion of the universe. The original spectrum was reddish/infrareddish. The spectrum spreads out and spreads out and spreads out. And the current peak wavelength should be in the microwave part of the electromagnetic spectrum, and it is. The first measurement of this cosmic afterglow occurred in 1964 by accident. These people killed a lot of pigeons. They thought that maybe the microwave hiss they were hearing in their observation device was caused by pigeons pooping on it. So there was mass pigeon slaughter, and yet the hiss continued to exist. So yeah, the Big Bang Theory appears to be true. In order to map the sky, we need to use a 2D projection of the entire sky. This is kind of like mapping the spherical surface of the Earth like an oval. And there is a cosmic microwave background radiation. Part of this is reddish, because that's the bit we're approaching on our orbital path, and part of it is bluish, because that's the bit we're receding from on an, vice versa. Part of it is bluish, because that's the bit we're approaching on our orbital path. Part of it is reddish, because that's the bit we're receding from on our orbital path. Correct for that, and you get this. So this is pretty homogeneous. There's tiny little temperature differences in it, and they really aren't very big at all. But we think that these tiny little temperature differences are largely responsible for the formation of large-scale structures everywhere in the universe. So some places are a little more matter, and some places are a little less. The higher gravity and the more dense regions cause the cosmic microwave background light to experience a slightly higher gravitational redshift than in other locations. Hence, the wavelength of the cosmic microwave background radiation varies slightly. And in that slight variation, we see enormous galactic structures. So each dense spot was the birthplace of billions of stars and galaxies. And so z equals 10, which is pretty much the limit of what we can see. Z equals 3, z equals 1, z equals 0. The universe has been contracting and contracting and contracting in order to be closer to local spots of high gravity. So, yeah, that's where we are in the history of the universe. And then I'm going to skip Planet of the Day. It's just about the Kuiper Belt. I'm sure you all know, or if you don't know, look into it. It's great. Super fascinating. I'm going to skip this element of the day because y'all have taken chemistry. So, cosmology is a study of the evolution of the universe. We want to know, what did the universe look like right after the Big Bang? How the universe changes, it expands, and what will the final state of the universe billions of years from now be? Right now, the universe is expanding. The Hubble constant tells us by how much. Remember, it's 75 kilometers per second per megaparsec. So 1 megaparsec away, that galaxy is moving away from us at 75 kilometers per second. 100 megaparsecs away, that galaxy is moving away from us at 7,500 kilometers per second. So what could cause the universe to slow down? What could cause the universe to speed up? Gravity could cause it to slow down. And as to what it could cause it to speed up, we don't really know, but it seems like something is. The universe is full of stuff, and all that stuff feels a force of gravity, and this force wants to pull the universe back in upon itself. So, Big Bang, if the universe were to be pulled back in on itself, we'd eventually see a big crunch. This is, by the way, not going to happen, as far as we can tell. So, is there enough matter out there to make the universe recontract? And the answer is no. Everything's spreading out so rapidly that there will be no going back. We shall not reconverge. By this point, we're pretty sure. But let's imagine that it was for a moment. The critical density would be the value that the current density would have to have such that the universe barely stops expanding far, far into the future. This would be called the steady state universe. And that would be the steady state universe, that eventually gravity and the expansion of space-time would kind of arrive at a kind of peace, and everything would be basically the same size. But that is not what appears is going to happen. What appears is going to happen is that the expansion of the universe will expand and expand and expand. It'll go stronger and stronger and stronger. And everything will just get flown apart from each other very rapidly. So between these three curves, the one that is in black is the one that's actually correct. The size of the universe will continue to increase. It will not recontract. It will not end up at a regular predictable size. So when Albert Einstein was writing down his equations of general relativity, he noticed that any universe containing matter would be forced to collapse by gravity. At the same time, people thought the universe was static, i.e., it remained more or less the same size. So in order to keep the universe static, he added a constant to his cosmology equations, called the cosmological constant, made up for no reason besides to keep the universe roughly the same size. Once Hubble discovered the expanding universe, Einstein took the constant out. In retrospect, Einstein referred to adding this constant as a huge mistake. Instead of using lambda, capital lambda, to keep the universe static, he could have realized the truth, that a static universe is nearly impossible. By the way, I have no idea if that picture is true. It might be. Seems more likely it's just a Simpsons reference. So, from the 1990s, we know the universe is not only slowing down, but it is actually growing bigger and bigger and bigger, by which I mean that the expansion of space-time is increasing. So more and more space is being created every moment than was created every moment before that. So things are flying apart more rapidly all the time. So what could cause the universe to accelerate? And the answer is something we call dark energy. And we're not really sure what dark energy is going to do to us. Like, it could suddenly change sign and make things contract instead of expand. That would be the big crunch when everything gets pulled together. Dark energy could stop expanding and remain more or less constant, in which case the universe gets an opportunity to die with, I don't know if we want to say some form of dignity, but it gets an opportunity to die with everything cooling off and slowly becoming just inert matter. On the other hand, dark energy could continue to be stronger and stronger as it's doing right now, in which case it'll eventually get to be enough of a force that all matter gets torn apart by it. That'll be the big rip. Assuming a constant amount of dark energy, which seems not to be true, it seems like there's more dark energy every moment, the universe would just end up in what's called a big freeze. Galaxies get very, very far apart until we can't see any other galaxies, only the Milky Way, which, by the way, this slide is wrong. By this point, it would be the Milky Way and Andromeda and the Triangulum Galaxy all collided with each other and having sucked up all of the tiny little dwarf galaxies anywhere nearby us. So stars in the Milky Way should form normally for about 1 trillion years, but eventually we're going to run out of gas to form new stars. No more new stars. Slowly, existing stars will run out of fuel and cease to shine, turning into white dwarfs, neutron stars, and black holes. If, and this is a big if, protons are unstable and decay, eventually these dead stars will all turn into black holes, which will evaporate via Hawking radiation and cease to exist. However, since the idea of protons decaying has been floated, we've been watching protons very carefully, and none of them seem to have decayed yet. So it's getting less and less unlikely. So the expansion rate of the universe depends on 3 factors: the amount of matter slowing down the expansion, the amount of dark energy speeding up the expansion, and the shape of space-time. We pretty much know what the shape of space-time is now. It's flat. But let's consider other options. It could also be open. If the universe was open, then if you had a sufficiently large triangle, the sum of the angles would be less than 180 degrees. Or it could be closed. If it was closed, the sum of the angles of the triangle would be greater than 180 degrees. A more reasonable way of looking at this might be to imagine 2 lasers being fired off perfectly parallel to each other. The universe is flat. Those lasers will always stay parallel. The universe is open. Even though they were fired perfectly straight relative to each other from the get-go, they would eventually converge. If the universe is, if it's open, they would eventually diverge. And if they were closed, it would eventually converge. So it sure seems like space is flat. And then as time has passed, we've learned more and more and more about the structure of the universe. We've known about dark matter for a long time due to the weird way that galaxies rotate. It takes a huge sphere of dark matter to explain that. Galaxies do not rotate via anything like Kepler's laws. And then once we figured out the universe was flying apart faster and faster and faster, we had to include dark energy. And that is the majority of the energy content of the universe as far as we know right now. So, y'all good at math? Here's the math. We got matter density, curvature, and dark energy, all determining what the Hubble constant is. So it's not just a constant that relies on how far away things are now. All of a sudden it relies on the curvature of space-time, how much dark energy there is, so on and so forth. It's pretty disturbing that only 0.4% of the universe is stars by energy. 3.6% is intergalactic gas that is yet to become stars. 22% is dark matter, and we don't have any idea what that is. But we know that it's basically something that exerts gravity. And 74% is dark energy, and we really don't know what that is. So back to the original picture. We have something, whatever it is, that caused the Big Bang. Eventually, electrons are held onto by protons. Again, that lets light pass through them. Takes a while. Eventually, stars start to form, and then galaxies. Dark energy, or something that's akin to dark energy, seems to have made the universe expand very quickly in the early period of our history. And then it slowed down a lot. The very fast early expansion is called inflation theory. And then it slowed down by a lot, and now it seems to be speeding up again. What does it all mean? Let me know if you figure it out. You can get a Nobel Prize. So inflation solves a bunch of problems with the original theory of the Big Bang. One of them would be the flatness problem, one would be the horizon problem, one of them would be the magnetic monopole problem. The flatness problem indicates that any deviations from perfect flatness should grow over time. And so it's weird that we see an almost perfectly flat universe about 14 billion years after the Big Bang. Something must have caused the universe to be so close to flat, or else it's nearly impossible for the universe to still be flat today. But if the universe expanded very, very, very quickly, there was no time for the universe to become not flat. And then the horizon problem. Why is the cosmic microwave background radiation so smooth? Everywhere we look, it's almost exactly 2.725 Kelvin. So again, if the universe expanded so quickly that nothing at any time to communicate with anything else, then the fluctuations associated with matter interacting with matter would be completely smoothed out, because nothing had time to really touch anything else before it was ripped apart for forever. And that's how it solves the horizon problem. Most weirdly, how does inflation solve the magnetic monopole problem? So some theories in physics predict the existence of particles called magnetic monopoles. These particles should have been abundant and easy to detect. However, we've never been able to detect one, period. Because inflation makes our universe so big, it is possible that these magnetic monopoles are now spread so thinly that we would only have a tiny, tiny, tiny chance of ever seeing one. Last time you're going to see this picture. This is the canonical boring poster of what you might have on your room if you want to indicate an interest in the universe. So, things started out hot and tiny. Eventually, they got big and complicated. And here's the final diagram of size versus mass. And so we have stars, the sun, neutron stars, galaxies. If you get any more dense than that, it's black holes. Got the nucleuses of atoms. If you get any smaller than nucleuses of atoms, then everything is uncertain, and matter can pop in and out of existence at any moment. That would be the realm of quanta. Then nothing is bigger or more massive than the universe itself. As a matter of fact, I'm really confused by why that isn't at the exact point of the triangle. But so it goes. So what does the universe contain? Almost entirely dark energy, atoms, a little bit of dark matter. However, if we look back over an unimaginably long time, it was just dark matter, some neutrinos, some photons, a little bit of atoms, and dark energy had yet to really assert itself as a force. Again, we have no idea what dark energy is. So, who knows what it's going to do next? The way that we investigate these kinds of things is we accelerate particles to super high velocities and slam them into each other. High velocity means high temperature. The higher we can get the velocity, the more closely we can simulate the extremely high temperatures of the early universe. So here's CERN, which is currently the premier particle accelerator in the world. It's in Switzerland. It's way better than Fermilab, which is in Batavia, which is right outside of Chicago. So why did the Big Bang happen? Is it the only Big Bang to have ever happened? Is our universe the only one out there? I have no idea. In theory, there might be other universes, but we have no reason to assume that there necessarily are any. And then, final planet of the day, the Oort cloud. I'm not going to play those videos. You can play them yourself. All right, now I'm going to see if I can upload all this stuff.